So I will tell you about a bunch of different topics in self-assembly of colloidal systems, and this is work that involves both a computational component and an experimental component. So the computational component has been performed by people in my research group, a postdoc and three students. And then the experimental work that complements that is done in the research group of Steve Grenick. At the time he was at the University of Illinois. He has now moved to Korea. And one of his students, Jing Yan. So even though I will speak about colloids today, I actually have an interest in a lot of different topics involving self-assembly that ranges from the organization of bacteria on surfaces, so the initial stages of biofilms, encapsulation of plasmid DNA in particles that can be used for gene delivery, assembly of tetrapodal particles, the role of self-assembly in the replication of viruses and how you can interfere with that, and lots of similar topics in the colloidal realm. So let me start with that, and I start just like yesterday. I really liked it when I saw that with Leonhard Euler. I also would like to start with a little bit of history. And so this is arguably the most famous scientist of the 17th century after Newton, and that's Christian Huygens. And trust me, that's the proper Dutch pronunciation. I know. So he discovered, and there's a whole story around it which I will not go into right now, he discovered what we now know as the phenomenon of synchronization. So this is the idea that you have multiple independent oscillators that then are weakly coupled. So he started this with pendulum clocks, and I want to emphasize a weak coupling means just that. So imagine you have two pendulum clocks side by side and you couple the two pendulums. That is not weak coupling. Then of course if you attach a rigid beam between the two pendulums, they move in sync, that's obvious. A weak coupling in his case was the fact that these two pendulums were mounted on the same wooden wall. And so that phenomenon where you have this weak coupling can lead to the two oscillators finding a common frequency and also a specific phase shift. And there are numerous examples in nature. This ranges from applause after a concert. At some point people start to applaud in sync, and they don't agree on this, it just happens. Another example is that of fireflies, which surely don't talk to each other, but at some point fireflies can actually start to blink simultaneously. Another example is in coupled Josephson junctions, so that's something in electronic devices. And there are many, many other cases. The question now is, does that interesting phenomenon, which is mostly a mathematical topic, have anything to do with self-assembly? So we set out to try and investigate that, and we did that using Janus particles. Janus particles are spherical particles where one hemisphere has a different coating than the opposite side. And in this case, the coating is on a silica particle, and the coating itself is a hemisphere that is made out of nickel. It's a very thin layer, so thin that the nickel actually acts as a paramagnet. Now this particle, and so the picture is totally exaggerated, right? This is a very, very thin coating compared to the diameter of the particle. Particle is a few micron in diameters. This particle is now put into a magnetic field, and you already have a complicated situation there. Because of the hemispherical shape, the magnetic response is different along, let's say, the equatorial plane and the plane perpendicular to that, or the axis perpendicular to that. So this red arrow is not a magnetic field or a magnetic moment, it's just what I call the director of the particle. So you get a strange situation that you put a magnetic object, a paramagnetic object, in a magnetic field, and the magnetic moment induced will not be parallel to the field. Very strange, very counterintuitive. So then you get a torque, because the magnetic moment of the particle doesn't align with the applied field. So the particle will start to rotate spontaneously. Now to make it even more complicated, we then rotate the magnetic field. So then the particle is constantly trying to catch up. And this magnetic field is precessing around what I call here the z-axis, and there's this opening angle theta. That's an important thing to remember, but I'll remind you. So what happens if you do that? It is so complicated that it's best illustrated with a movie. And so the idea is as follows. The screen is the XY plane. The Z-axis is coming out of the screen. Sorry. And the microscope image is a top view of the particle. The other three panels will just show, let's say, the north pole, so the top of the magnetic side of the particle as we move along. So here you see what happens. The magnetic field is rotating counterclockwise, and so is the particle. But the particle is rotating at a completely different frequency than the field itself. In the meantime, the particle is nodding up and down out of the plane. The motion is aperiodic. Of course, I just looped the movie here, but it's actually an aperiodic motion. And you see that the top of the particle is making this funny oscillating behavior. So that's already complicated, but at that point, it's just a toy, right? It's a game. It has nothing to do with synchronization or self-assembly. Nevertheless, we have to have some idea about what's going on. And it turns out it's actually completely possible to understand this. I will not go to the equations here, but basically, you can describe this into a system of two coupled differential equations that can be solved, has been done before, and you find exactly this nodding motion. So that's completely understood. The interesting thing, though, is that even though this motion of the particle is controlled by the magnetic field, there's still a certain degree of freedom. And, well, I already said this, so let me point out one thing. The motion of the particle, even the rotational frequency of the particle, can be changed solely by changing the angle of the magnetic field with the z-axis, not the frequency. So you change the angle of the magnetic field, leaving the frequency alone, and the particle will start to spin slower or faster. However, there's this important property. Here you see a top view. So the z-axis is coming out of the screen. The particles are moving around. This is just a snapshot. And you see that the magnetic side, this nickel side, which is opaque in the microscopy image, so it's the black side. Those black sides can point in different directions. So we have oscillators here, but they still have a certain degree of freedom, the so-called phase freedom. This is a mathematical term, but the bottom line is it's an important ingredient, a crucial ingredient to get synchronization. So what do we have here now? Now it gets interesting. We have particles that oscillate. We have particles that have a certain degree of phase freedom. And we have particles that carry a magnetic moment that allows them to interact with each other. So what happens now? To clarify that, we started then to do simulations. And if you have some experience in simulations, then you might frown or laugh or wonder about these numbers. 50 colloids only. People now do simulations of 100,000s of particles. So why is that? Well, for one thing, you have to follow these particles for very, very long times. These particles gradually have to interact, adapt their motion, and so on. But on top of that, the really tricky part is that the magnetic moment of each particle depends not only on the magnetic field, which changes over time, it also depends on the magnetic moments of all the other particles. And those influence each other then again. So you need a so-called self-consistent calculation, and that makes this incredibly expensive. However, the good news is 50 particles is completely fine. That's enough to see what's going on. And I'll illustrate that to you. So let's start just with two particles. Two particles that are moving around just as you saw in that movie, but now in a simulation. And it looks exactly the same as in those movies, experimental movies. But now the particles contain or carry these magnetic moments, which are overwhelmingly, but not completely, oriented parallel to the equatorial plane of the Janus particles. So these yellow arrows. And over time, particles that are a little bit separated will attract each other because the magnetic moments attract. And then they will orient themselves while still rotating and nodding in this magnetic field that's moving around. They will orient themselves such that there is an alignment. You get something that if you would proceed in making this longer, you would get a sort of zigzag chain. A zigzag chain in which the particles still try to move and oscillate. So that is the first step towards synchronization. So now what would happen if you would increase the density and not just have particle pairs, but actually entire groups of particles? It's quite surprising, and I think it's nicely illustrated in this movie. So this is almost real time. The system had been developing here for maybe only a couple of minutes, and you see the particles have aligned in these zigzag chains, but then these zigzag chains start to interact with each other. And so now the magnetic field is precessing around the z-axis, which is now running from left to right. And what you see is that you get the formation of these tubes. And these tubes become very, very regular. Because of the lack of time, I will not wait for another 5 minutes, but I guarantee you that these movies end with completely ordered chains. Tubular structures that are completely ordered. And that's illustrated in this set of pictures here. So it turns out, over time, you end up with a whole zoo of tubes of different diameters. And in those tubes, the particles are ordered in a completely regular pattern. So the only difference is here that you have different diameters. In fact, the tubes that you get here, they have a nomenclature here, 220, 330, and so on, that is actually related to the classification of carbon nanotubes. You start with a graphene sheet, and you roll that up, and you can roll it up in different directions. You can also create tubes of different diameters, and that is given by those 3 numbers. In this case, you have no chirality in the tubes. That's why the last number is always 0. So the only thing that happens is that you get different diameters, and that's the first and the second number. Okay, well, if you're working in self-assembly of colloids, you know, every week there are dozens of papers of new ordered structures that self-assemble, and nobody gets that excited about it anymore. But remember, this system is still residing in a magnetic field that is moving, a magnetic field that makes all the particles move around as well. So how can that be combined with these regular structures? This is something where simulations can give you a lot of insight, and it turns out ultimately even explain what's going on in the whole formation of these tubes. So first we start with a simulation movie. This is the top view along a so-called 330 chain with very high time resolution. So what you see is that even in the tube, the particles are still moving around. They still make this nodding motion. If you look carefully, you also see that the 3 particles that sit in this triangle, that's like a cross-section of the tube, are exactly phase shifted by 120 degrees. They do this spontaneously. And that's illustrated by these 3 curves, which you see are perfectly phase shifted. If you would take another look, you would see that 2 particles in this triangle, so take the top 2, are perfectly phase shifted with respect to the particle below them in the next layer. And so the whole tube has this perfect phase shift from neighbor to neighbor. At the same time, you see, if you look closely and you watch over time, that this tube is slowly moving or rotating counterclockwise. You can see that better if we actually take a simulation in which we speed up time a little bit, and I'll show you that here. And you see the particles are nodding very quickly, and the tube is rotating counterclockwise. Now let me stop this movie before anybody gets a seizure, because there's something very interesting going on here that goes to the heart of what holds this whole thing together, what makes it rotate, and what ultimately explains the stability of these tubes, and that brings us then to the topic of synchronization. If you look closely, you see that these particles have their blue, that is the magnetic side, not facing exactly toward the center of the tube, which would have been the state of the lowest energy, but they're lagging slightly behind, indicated by this angle psi. It turns out that that is a necessity. The particles find this lag psi by themselves. Namely, the particles want to rotate in the magnetic field, right? If they were left alone and not part of this bigger structure. But if they did that, and the tube itself would not rotate, then in no time the blue side would point to the outside of the tube. But that's not possible. The blue sides carry the magnetic moment that keeps the whole thing together. So as soon as that would happen, the whole thing would fall apart. So the only answer, the only compromise that's possible is if the tube itself rotates as well at exactly the same angular frequency as the individual particles. So this lowercase omega must be the same as this uppercase omega. So the whole tube must rotate such that the blue side remains facing inward. But why would the tube rotate? That's only possible if there's a global torque on this cylinder. You get that torque by having this particle not facing toward the center, but slightly off. That leads to a net magnetic moment of the whole cylinder, which then is dragging the cylinder around as the magnetic field rotates. So the particles in the cylinder and the cylinder itself find an angle, a lag angle psi, that gives you a torque that's exactly enough to rotate the whole cylinder, given the drag of the surrounding solvent, at a rate which is equal to the spinning rate of the individual particles. And so you can write down a motion or an equation of motion for that. And so if you do that, you end up with this equation. This is d psi dt. That's the change of this lag angle over time. It depends on how fast the individual particle wants to rotate and on the drag that the cylinder is experiencing. That's those zetas. And then on top of that, the magnitude of the torque, which depends on that angle psi. Now, you may never have seen this equation before, and I had never thought about it until I started on this topic. But then I realized that this equation is actually very famous in the field of synchronization. This equation was first written down in the late 1940s by Adler. He worked at the time for General Electric, and his real claim to fame outside the field of synchronization was that he invented the first usable remote control for televisions. But of course, that's probably a bigger contribution to mankind than this equation. But nevertheless, this equation itself also became quite famous because it describes all sorts of synchronizing systems. Now realize, we don't want that angle psi to vary. We want a stationary state where the whole cylinder is rotating. So then you can do a very simple analysis simply by looking at this. Obviously, the left-hand side must be 0. The psi dt must be 0 if psi is constant. And then you realize, that is not always possible because this second term can only become so large because the sign, of course, is bounded. That means that omega-3 cannot be too large. If omega-3 is too large, you will never get the right-hand side to 0, and so you will not find a stationary solution. But now remember what I said in the very beginning. Omega is controlled not just by the frequency of the field. I don't want to touch that, then it becomes too confusing, but just already by the opening angle of that precessing field. So if that field is rotating around the z-axis, I'm only interested in the angle of the precessing field with the z-axis. So let's see if we can exploit that. It turns out it works perfectly. If you change that opening angle, here let's first look at the inset, and you see if the opening angle becomes larger, the particles start to rotate faster. That means also the cylinder should rotate faster. It needs a larger torque, which means this angle psi has to grow. And it does just that. But it cannot grow too far, because then at some point, the blue side is not even pointing to the center of the tube. So you don't have anything that keeps the whole tube together. And that's indeed exactly where you see this collapse at a given theta. We can look at it in another way. We can define an order parameter that tells us whether this tube is even a regular object. And this order parameter is more or less equal to 1 at all angles until, again, you hit this critical angle, and then the order parameter drops. This is the point where the particles want to spin so fast that the tube has to rotate like crazy. You need a huge torque. Psi becomes so large that it's just no longer a stable structure, and the whole thing flies apart. And we can then finally also look at the blue symbols. That's the difference in angular rotation frequency of the individual particles and the cylinders as a whole. And of course, that has to be 0, and that's exactly also what disappears at this critical angle. So now we see that synchronization, this mathematical topic, completely describes the self-assembly, the structure, and the stability of these structures. And the nice thing is now that we actually can exploit this. If you do self-assembly, this happens in many situations, you end up with many ordered structures. And it is not true that these are all free energy minima. Well, they are local minima. The tricky point is that they are separated by huge free energy barriers. So even if one structure is not the absolute free energy minimum, you will never get out of it and go to the true minimum. So that means that you do this self-assembly and you end up with a whole zoo of self-assembled structures. And there's very little control you often have on which of these structures dominates your final collection of structures. Here we can control that. Because this angle theta, and this is just of course an illustration, this angle theta controls the stability of tubes. But tubes of different diameters, which you would end up with, have different critical angles theta. Because they experience a different amount of drag, they need a different torque to move around at a certain speed. So if the particles favor a certain frequency or a certain rotational frequency, then only certain tubes can match that. And so you can change the opening angle of the precessing field and in that way control which tubes are stable and which are not. And that's shown here in this plot here. Different colors, so this is experimental, so that's why it's not, super pretty. But you see definitely that at low angles theta, we see predominantly these green structures. These are huge tubes. And these then gradually disappear at high angles. And you see this is over a fairly narrow angle window. And by contrast, if you have larger angles where the particles move faster, the tube has to move faster, the large tubes, the fat tubes cannot keep up, and you indeed select predominantly the narrow tubes. So that is an example of how synchronization describes self-assembly in a way that at least I totally didn't anticipate, and how you then even can use this insight to create self-assembled structures of specific shapes. Okay, so in terms of the technical side, this self-assembly has also a specific thing that's going on. Namely, we have these interactions that do not depend just on pairs of particles, but these are interactions that have to be computed self-consistently. That makes it so expensive. Exactly the same problem goes on in another area of self-assembly, and that I would like to spend the last 10 minutes on. Because it's something we worked on in the last few years, and I think the results have a very broad application. So, in fact, most topics in self-assembly of colloids don't rely so much on magnetism, but on electrostatics. In water, almost anything is charged, and of course that's due to the high dielectric constant of water. And that's also why in biology, of course, charges play such an important role. The tricky point is, if you think about it for a little longer, then you realize I have these objects often made out of organic materials, silica colloids, polystyrene colloids, and so on, that reside in a solvent that has a different dielectric constant. It is water or some organic solvent, it doesn't matter. It is typically a dielectric constant that's different than what the material has. And then from basic electrodynamics, you know there is polarization on these objects, polarization charge. As soon as there's a dielectric mismatch and there are charges, there are polarization charges. And my statement or my claim is that even though everybody acknowledges it, it gets almost completely ignored in self-assembly. And I know why. it is super complicated to calculate. It's expensive and it's difficult. But I could at least argue that it would be better to ignore it after somebody at least made an elementary assessment of how big or how small these effects are. And so we set out to do that. And we're not the only ones. The good news is that a number of groups around the world is actually working on this right now and trying to incorporate it in all sorts of molecular dynamics and Monte Carlo simulations of various systems. The next good news is also that it's not true that we don't understand it, right? I mean, since Maxwell, we know exactly how to calculate it. The problem is that it's difficult. We have an electrostatic potential, and we all know that it can be computed from the charges in the system. If you know all the charges in the system, you can compute electrostatic potential anywhere else. And maybe you haven't seen it in this form, but it basically means you look at every charge and you look at the distance to those charges, and that's all there is. But there are two more terms, and they depend on the polarization. This is surface polarization that is at dielectric interfaces, where the dielectric constant goes from one value to another. Let's say from silica to water at the interface. And then there is this last term, that's bulk polarization, that occurs when the dielectric constant of a material varies continuously. The tricky part, obviously, is that the magnitude of P, the polarization field, depends on the potential. It's induced by the electric field. So this has to be computed self-consistently. And that makes it so time-consuming. What gets worse is that if these are dielectric objects, then the dielectric interfaces move around over time, and so you have to compute this over and over again. It's mind-bogglingly expensive. We can make things a little bit simpler by saying, well, let's assume that all materials have a dielectric constant, which is constant until it jumps to a different value. Then you go from three-dimensional problems to two-dimensional problems. This whole last term is gone. So let me just skip this slide in the interest of time and just tell you how one proceeds. The recipe is actually quite straightforward and has been seen by a number of people for decades now. This goes at least back to 1978. You have these dielectric interfaces, you make a grid of points at every interface, and you solve the polarization charge at each of these grid points. And that can be done, and there are then several approaches to that. Things evolved over time. Clever ideas were proposed, but the bottom line is, no matter how clever these ideas were and how original, none of them were fast enough to actually allow for dielectric interfaces that would move over time. Exactly what you would have if you have, let's say, silica colloids or polystyrene colloids moving around in a solvent. What we want is we want to know all the dielectric effects at any moment in time, and we want to include the forces and torques on all objects and see how they influence the self-assembly. So the last 2 years I've been working on that with a student and a postdoc, Daniel Simkowitz and Kipton Barros. And we came up with a method that is so efficient that it actually now allows us to do just that, this dynamic assembly of dielectric objects. Now, I will not spend time on the technical approaches, but I want to lead you straight to an example of where we can show that it really makes a difference and you get actually exciting many-body effects. And to illustrate that, I want to very briefly review something that whenever I show this to people, they're somewhat surprised until I remind them that this is in basic textbooks on, let's say, colloidal materials, electromagnetism or electrodynamics, and so on. This is in standard physical chemistry courses. If you have a dielectric object and you bring a charge, let's say a negative point charge, to the surface, you induce a charge on the object. The total charge on the object must be zero. You don't create charges. You just reorient dipoles. But closest to the point of where this negative charge approaches, the induced charge is negative. The charge induces its own repulsion. If the dielectric constant of this colloid is lower than the surrounding medium, think most materials in water. But take the same material and put it in a very low dielectric constant solvent, an organic solvent, acetone, anything like that. Take the same negative charge. It actually will induce its own attraction. It will induce a positive charge on the part of the colloidal surface closest to the negative charge. So there's a lack of symmetry here. And we can see how that actually affects self-assembly. So to study that, take a system of large and small particles, oppositely charged, and put them in a solvent. And we bring this to very low temperatures so that you get strong electrostatic attractions and compared to KT. And we see what happens. And so then, depending on the dielectric background, the solvent chosen, you either get particles that, well, they are attracted to each other, but that attraction is either weakened or strengthened by the dielectric effects. And let me show you what we find if we do that. First, we of course started to look at pair correlation functions of a whole assembly of hundreds of these particles and watch them over time. This is expensive now because you have very low temperatures, things move slowly, and we have to recompute all the dielectric effects at all times. So to give you an idea, on one colloid, one of these blue spheres, actually we compute 300 to 400 dielectric charges scattered across the surface. So even 100 colloids then already means around 40,000 charges. So it suddenly becomes a very big system. What we find is that depending on the dielectric contrast, you either get pair arrangements like this, so the two colloids, which carry the same charge, are held together by two small particles which hold the opposite charge that kind of bracket the touching point of these colloids. But if you switch the solvent to something that has a low dielectric constant, then the colloids jump into this configuration with the small charged particle in between. And the reason that that happens has to do with the interaction of all the polarization charges on the colloids, which I don't show here. So what does that mean now in terms of actual structures? Can we go beyond pair correlation functions to actual structures? So that's the last two slides that I want to show you. First, let's take these colloids, let's say in water. What you get is a sodium chloride structure where the small negatively charged particles hold together the positively charged particles. So there's this orange glow on the particles because the color coding here indicates the total charge, so free charge and induced charge. So the whole thing is held together in a sodium chloride structure, but you see that the small particles actually don't want to touch the colloids because they induce their own repulsion. They kind of hover in these interstitial spaces. So nevertheless, they hold the whole structure into a stable configuration. And you can think of lots of interesting things now. For example, what if you apply an electric field? Would the small particles start to move around this structure that they held together themselves? Who knows? Now, we take the same system. The only thing I'm changing is I'm switching out the solvent. And look what happens. So this is this effect that everybody ignored, right? There's only dielectrics that change things. Suddenly, this structure switches to this arrangement of what at first sight look like polymers. These, of course, are not polymers, but these are string-like structures. So there are 2 points here. Not only is it, in my view, very exciting that dielectric effects really qualitatively change things. So these effects that have been consistently ignored actually make a real difference. But secondly, the structures that you get here actually arise from a many-body effect. So that's often exciting because it means that your intuition is out of the window in many cases. But this is one of those many-body effects that you can actually understand in 1 minute. Imagine that you start from a single colloid and you take a single small particle. Well, it will be attracted to the particle because they have opposite charge. So it goes to any point on the colloidal surface. Let's call it the North Pole. Now a second small particle comes along, it's also attracted to this colloid, right? So another blue particle comes and it also gets attracted to, let's say, this colloid. So it wants to sit at the surface, but it doesn't want to sit close to the first blue particle because those have the same charge. So the second blue particle goes to the South Pole. So far, so good. But then what? Now there are these dielectric effects. And remember that in this case, the blue particles induce their own attraction. So they bring positive charge to the contact points. But dielectric charge, as I said before, is not created. It's just dipoles that move around. So as soon as that happens, as you get positive charge induced, let's say, on two sides of the particle, then the entire remaining surface of the colloid carries the opposite charge. It becomes negatively charged. It has to be to make the whole surface neutral, dielectrically neutral. But that means that another small particle that comes along has nowhere to go. It doesn't want to go to the North Pole. It doesn't want to go to the South Pole because there are already negative particles there. And the equator is negatively charged. So a third blue particle has no choice than to go to a different colloid. And that is how you get this formation of these string-like structures. And at first, of course, we were excited to see this, but I wasn't sure whether this is completely real or whether it's observable in experiments. But then I spoke to several people who do self-assembly, especially of nanoparticles, where these dielectric effects are much larger because they get spread out over much smaller surface areas. And they sent me a whole list of papers of the last decade where experiments of nanoparticles in organic solvents actually observe string-like structures. And it's very interesting. If you read those papers, there's a lot of hand-waving and some muttering about van der Waals interactions may be causing this, but no true mechanistic explanation. And by now I've become quite convinced that quite a few of these string-like structures in those systems actually can be explained by this mechanism of dielectric effects. So with that, I've come to the point where I've shown you two completely different mechanisms that I hope change a little bit the way you think about self-assembly, how many body effects really lead to counterintuitive things that actually can be exploited to control dielectric or magnetic structures. So to summarize, I showed you these paramagnetic Janus particles that illustrated that self-assembly can be coupled, this field that we are familiar with can be coupled to this mathematical field that we don't think about so much, namely synchronization, and that we can even exploit it. We can now rapidly reconfigure structures, we can selectively create and destroy structures, and we can even maybe create structures where the internal components are moving in a synchronized fashion. So if you think about those tubes, there's maybe one last point I would like to make. Those tubes in which the particles are moving in sync, exactly phase shifted. You can imagine to create structures there that actually can almost work like worm wheels or tubes, micropumps. And then finally, just showed you in the last 10 minutes, dielectric effects now can be incorporated and really make a difference. So with that, I'm ready for any questions. Thank you.